Hello, we are Group 5 and we've implemented the real-time color correction for optical see-through HMD displays for the shading approach. We are Group 12. So as a summary, most optical see-through HMD use the optical binder blending with the physical environment with digital information. The light comes from the background, which makes the light original from display while causing the color blending problem. So our ideas comes from color reference. The display from naked eye should be as vivid as expected before. For example, this is the screen blending before and after collection is to be perfect effects on TV. So the current challenge is that how to compute a composition image, minimizing the effects of color blending between the display image and the environments, and also the color correction algorithm based on color blending, and convert the color correction algorithm to shader in Unity, and apply pixel vertex based on shader to AR environments. So here's our color correction algorithm for HoloLens. The first one is colorimetric, second is photometric, and third is LUT based. As for Unity rendering pipeline, there comes from the calling, rendering, and post-processing. And for example, this is destination shaders texture, and we learn from the background image about the current luminance, and then after do the filtering, we start to per pixel operations, and then followed by the LUT-based color corrections. So the challenge is then how to align background image captured from camera to the matching screen space, and calculate the color of each pixel with the blending problem. And the fragment shader is executed per pixel by geometry to texture. And also, it's very hard to optimize in calculation performance for each pixel of HoloLens. For example, the upper right is colorimetrics, and followed by photometrics and LUT. So let's move on to colorimetric method. So it's about how to compute compensations of the luminance of the background. We take samples and then to calculate average luminance from RGB values and add to virtual objects. So here is a short video to demonstrate the simple colorimetrics method. For example, once I move around, you can see the colorimetric shaders on the screen, and I can move around. Here's the shaders effects. Okay, and second is photometrics compensation. We set a constant parameter k denotes the fraction of the case. So for every pixel, there is the Ri denoted by the virtual objects and multiples by the virtual for each pixel minus the background information. So please note that if the virtual image is dark itself, the background is bright, Ri might not be able to notice anymore. So here's the photometrics idea. Next, I'm going to show you a few examples. Um, because it's very hard to rendering to record. So we took the videos by our phone, and you can see it's currently processing, conducting the photometric renderings. So for example, I just the screenshot I took from HoloLens. Once we turn off the light in the room, so the light comes from the roof, shines light on the cubes, and by the other face is stuck. So once I turn on the light, you can see the shaders come to green because it's very similar to the neighborhood color. And then I turn on the light, much lighter, and you can see it's turning to gray and yellow. And then turn off again, it's becoming dark. And this is on the dark situations. So followed by the last method is IoT-based color correction. You can see there are different levels of IoT methods. For example, 0, 0.5, and 1. And here's different artifacts. For example, how to correct IoT. So the corrections is that first capture original image or use Photoshop to run the color image to make max friendly, or generate IoT, then import to Unity. So here's a short demo. For example, as you can see, the shaders updating. So conclusions, we implement 3 color correction method and deploy on HoloLens. Thank you.